Let's talk about Newton's method. How does it work? What is the idea behind Newton's method? Okay, what do we have? We have a continuous real valued function. And we are looking for the root of this function or the roots of this function. What is the idea? If we have an initial value, one initial value, only one x0, then we can evaluate that function and we can find the derivative and the tangent to that function. What do we know about the tangent? We know that the tangent is very close to the function. So if we have the tangent, we can check where is the root of that tangent, and this is an approximation of the root we are looking for. But if we have this approximation, we can iterate that process. We can say, okay, maybe, most likely, this is not really the root of the function. So let's evaluate this function. Let's find the tangent here to that new point. Let's find the root of that tangent. And then we have a new x3 value, which is an approximation of the root of the function. And we see in that example that this algorithm will converge to the root of the function, and convergence is very, very fast. It's much better than the linear convergence we had for the bisection method. So if we want to formulate code, then we have to find the tangent equation. Okay, this is the tangent equation. Y is equal to some function value. So this function value. We need the derivative as well, and then f of x0, this is the function value, plus some deviation, and the deviation is proportional to the distance to x0, so the slope times x minus x0. Is this really the tangent? Yes, it is, because for x0, x is equal to x0, then we have function value f of x0, which is correct. Does this linear function has the correct slope? Yes, it has. So this is the tangent of our function. And what are we looking for? We are looking for the root of this tangent. So we set that to 0 and then we solve for x. So we set to 0, we bring that to the other side with a minus, we bring that to the other side with a divided by, and so we get this expression. Now let's get rid of x0 on the left hand side by plus, and so we have that. This is the root of the tangent. So this is mathematical analysis. We found the tangent, we set that tangent to 0, and we find that point. So given some x0, given a function value, given a slope, this is the root of the slope. And this is the new, the better, the improved x0 point. So x1 is x0 minus this. And we can iterate that process, and that means we iterate, we get the sequence, the recursive sequence, xn plus 1 is the last xn minus f divided by f prime. If you awake me at midnight and ask me for the Newton iteration formula, it is not so hard for me to remember, but it's hard for me to remember if f is the nominator or the denominator, or it's the other way round. But it's not so hard to remember, because if f of xn is 0, then we have the root, and then we will stay forever at the root. So this means, okay, we have a 0 divided by something which is 0, so xn plus 1 will be the same as xn, as it should be if you are exactly on the root. If it was the other way around, then we would have a divided by 0, and that is mathematical nonsense. Explodes, everything explodes, and okay, everything is damaged. So it has to be this way. But if you analyze that and you say, okay, division by 0, we will have a division by 0 if the derivative is 0. What does that mean? That means maybe you started here and then the tangent, there is no root. So derivative 0 means there will be no root of the tangent, and that's also what we have here. If derivative is 0, everything explodes. And if we are close to the root, we will get closer and closer, and the function value will become smaller and smaller. Okay, so this is Newton's method. What is the advantage? The algorithm is still very simple. It's even more simple than bisection was. The code will be shorter, but a little harder to understand. But now, with all I told you, I think it's also easy to understand. And the convergence is quadratic. What does that mean? Quadratic means if the distance to the root was a half, then next time it will be a quarter. Next time it will be 1 divided by 16. Next time it will be 1 divided by 256. And that means it accelerates. Linear convergence would mean a half, a quarter, 1 divided by 8, then 1 divided by 16, so 2 steps. And next time, coming from 1 divided by 16 to 1 divided by 256, which with Newton needs only 1 step, it needs 1 divided by 32, 64, 128, 4 steps. So if you are close to the root, you will get closer and closer. Okay, there's also a constant factor. We will later talk about the quadratic in detail. What does that mean? But please remember this idea. This is a big advantage. But be aware, before you can run the algorithm, you need some starting point, initial guess of the root, and this starting point has to be close enough to the 0. So we have a problem. If you have a function like that, and you want to find that derivative, you should not start with that point and not with that point. You should start with some point in the vicinity of the root. But how can you find this starting value? You are looking for the root, and if the function is of that kind here, then it will be hard for you to find good starting points. That's a big disadvantage. Let's see if we can overcome this limitation. We had this limitation for bisection, and now we have this limitation again for Newton's method. If the function is maybe of that kind, then it doesn't matter. You can use any point here on that interval and the convergence will be very fast. So for this kind of function, Newton's method is very good. Finding starting values is not a hard task, but for other functions it is, and especially if you have more than one root and you want to find all of them, then you have to use an initial starting point for every root. But how can you know them if you are looking for the roots? Okay, so this is a disadvantage here, and I emphasize this disadvantage. Maybe you check other YouTube videos and they will not discuss that with this tone, so that they tell you it's a big disadvantage, but I tell you the truth and the others don't. Okay, and the user has to provide the derivative on top to the function. So if the function is a complicated one, this is a very big disadvantage. Very big disadvantage, as we will see in our examples. Okay, so Newton's method is a standard algorithm when teaching numerics and teaching calculus, but the truth is it's not so often used in numerical algorithms, and the main advantage is you have to provide the derivative as well, and that might be a big thing to find. Here we have the code. The user provides f, the user provides the derivative. Okay, if we have computer algebra, it would be possible to do that implicitly, but using MATLAB you have to find the derivative by your own and pass it to the function. Provide some starting point which is close enough to the root we are looking for, and provide some tolerance. Okay, here we check if 2x are close enough, then we stop the iteration. You can think a long time about this this absolute value of x values. You can also think about, shouldn't we better check the function value of x, f of x0 and f of x1. Okay, but I decided to implement that way, but it's true, you can think a long time about that. Then I inserted some extra line, the real code, for real code, forget these lines, but for running the algorithm and getting a feeling of what happens, we should insert these lines. So we have a value, we have a function value, we take the last ones to be the old ones, and then we calculate a new position x and a new function value, and then we can check now if the difference is close. If they are close enough, then we leave the algorithm. So the code is very short. Okay, and now we can run our example. Natural logarithm of x minus x divided by 3. What is the derivative of natural logarithm 1 divided by x? What is the derivative of x divided by 3? That's minus a third. And let's start again with x0 to be 1. Then we will see the following happen, and after only 6 steps we have the root of the function, and in this case the function value is not very close to 0, but in numerical rounding range it's a 0. So we found the root in only 6 steps by applying Newton. So this is a great algorithm. Next example, rope around the earth. We have the function r squared plus rx plus a half, and that's squared, minus r divided by cosine x, and square that. What do we need? On top to the function we need the derivative. So what's the derivative with respect of x of that function? Oh, if you are not very used to finding the derivative in this case, I suppose you will provide the wrong derivative. It's not easy to find the correct derivative. Please try on your paper to find the derivative of that function. I also tried preparing that video, but the 100% certainty that it's correct, that's hard, especially signs. The sign here, what will happen to that sign? Will it keep being a minus or will it be a plus? I was very concentrated, and in the end I was confident that this is the derivative. But I wanted to be not only confident, I wanted to be 100% sure. What did I do? I asked Wolfram alpha, and he told me this is the derivative. Okay, I was not satisfied with this answer because there was some SEC. What is SEC? You can ask Wolfram himself and he will tell you it's 1 divided by cosine x, and then you can analyze if this is indeed the same as I have here, and the truth is it is, but you always have the feeling of, oh, I am not 100% sure, maybe there is an error with the derivative. So this is a big issue, providing the derivative by the user who wants not to calculate some derivative, he wants to find the zero, the root of the function. He has to provide the derivative, and that's a bad thing, Okay, so you can start with initial value 1 or with initial value 0, and if you start with 0, which is a very good choice, a much better choice than 1, it's much closer to the correct root. In this case, 0 is a non-allowed starting value because you get a root which you are not interested in. You get a negative angle which does not make sense at all. You know it's some angle between 0 and 1.5. And then the algorithm will give you a ridiculous nonsense root. So you have to provide good starting values, but good in the sense of Newton iteration. Okay, then if you start with 1, then the algorithm will indeed converge to the root, but it needs a long time. 25 steps is a long time in this case, and but you get the correct angle. Okay, so this is the story. Let's continue with our second equation for the rope around the earth equation, and this time we have tangent x minus 1 divided by 2 times the radius of the earth. And in this case, the derivative is not very hard. Tangent of x, the derivative is, okay, we can check that, and it's 1 divided by cosine squared, and the derivative of minus x is minus 1, and the derivative of some constant is 0. Okay, so this function is a function, and you will again need a large number of steps, and this is a surprise. Why do we need so many steps? Newton's method is a fast converging method, but unfortunately our rope around the earth problem brings us to equations with a very slow convergence, and the reason is that you have here a threefold 0. If that term was not present, this function here has a root, and also the derivative is 0, and also the second derivative is 0, and that implies a very slow convergence. Newton's method converges fast quadratically, but only if the slope at the root is non-zero. This is true in that case, but we are so close to a 0 slope, and on top a second derivative 0, that convergence will be slow, and we need a lot of steps. Okay, so this was our Newton's method, and we saw how it works, and we saw 3 examples. The first one is the standard example, okay, and the second and the third example is example which will produce unfortunately a slow rate of convergence. But don't confuse, Newton's method is a great idea. Please be able to find the roots by applying yourself 3, 4, 5 steps for some function and for some initial value.